3.5 billion years ago, Earth was a fiery, chaotic planet. What we now know as continents did not exist. The surface was dominated by molten rock, boiling oceans, and relentless volcanic eruptions. Thick clouds of ash and gases filled the atmosphere, creating a harsh and toxic environment. The young planet was still shaping itself, and the battle between heat from within and the cooling crust on the surface set the stage for the first landmasses to emerge. Amidst this chaos, the first fragments of continental crust, called cratons, began to form. These were ancient, stable pieces of rock, lighter than the surrounding basaltic crust, and they floated above the denser, molten mantle. The process was slow. Basaltic basalt cooled, melted, mixed with other minerals, and slowly recrystallized into silica-rich granite. Over millions of years, small islands of this granite accumulated, forming the very first continents. Standing on one of these early landmasses would have been surreal. Jagged volcanic peaks rose into a sky choked with orange-tinted gases. Boiling oceans lapped against sharp granite cliffs. Hydrothermal vents spewed mineral-rich fluids into shallow waters, providing the earliest habitats for microbial life. These islands were small, scattered, and fragile, yet they marked a turning point in Earth's history, the first stable land above the ocean. These cratons were not just rocks, they were the foundation for the future. Their emergence changed how heat escaped from Earth's interior and created new environments where early life could thrive. Over hundreds of millions of years, these islands grew, collided, and sometimes broke apart, setting the stage for the eventual formation of supercontinents. Today, remnants of these first continents can still be found beneath modern landscapes, in places like the Kopval Craton in South Africa, the Pilbara Craton in Australia, and the Canadian Shield. These ancient rocks preserve traces of Earth's earliest life, microbial fossils, and chemical signatures that tell the story of our planet's formative years. The birth of the first continents was slow, fragile, and violent, yet essential. Without these early landmasses, Earth might have remained a molten, ocean-covered world, incapable of supporting life as we know it. These islands of granite were the first chapters in the story of Earth's continents, the foundation upon which mountains, rivers, and eventually civilizations would rise. By 2.7 billion years ago, Earth had stabilized enough for the first continental fragments to grow larger. These early cratons drifted slowly across the molten surface, colliding and sticking together, forming larger, more permanent landmasses. This process marked the birth of Kenorland, Earth's first supercontinent. The planet was still volatile. Volcanoes erupted continuously, rifting created shallow seas, and the atmosphere remained thin and toxic. Yet these collisions were crucial. The combination of heat, pressure, and mineral-rich fluids produced more stable granite, thickening the continental crust. Island by island, fragment by fragment, small landmasses united, creating vast continental shields that would survive billions of years. Kenorland was not just land, it reshaped Earth itself. Its emergence influenced global ocean currents, trapped heat in certain regions, and created shallow coastal environments ideal for microbial life. Early stromatolites thrived in these shallow seas, leaving behind some of the oldest known fossils. These continents provided not just a foundation for future land, but also a cradle for life to continue evolving. Yet Kenorland was not permanent. Over the next several hundred million years,
It would break apart and reorganize into new continental configurations. But its formation proved that Earth's crust was capable of creating stable, long-lasting continents, the building blocks of all future supercontinents.
Around 2 billion years ago, Earth had entered a more stable geological era. The small, fragile cratons that had first emerged during the formation of Kenorland had now thickened and stabilized. These ancient pieces of continental crust, composed mainly of granite, had survived repeated collisions, volcanic eruptions, and relentless rifting processes. Their stability allowed them to form the cores of the earliest large landmasses, providing a foundation for the continents we recognize today. The formation of these stable continental shields was not a rapid process. Over tens of millions of years, the Earth's lithosphere gradually cooled, allowing granitic crust to accumulate. Magma intrusions from the mantle slowly hardened, while tectonic collisions between cratons caused compression and uplift, forming rudimentary mountains. These mountains, though eroded over billions of years, created varied landscapes that influenced water flow and sediment deposition. This period also saw the beginnings of shallow inland seas, where mineral-rich waters collected between stable cratons, offering ideal habitats for microbial mats and early oxygen-producing organisms. One of the most remarkable consequences of craton stabilization was the creation of long-lasting continental cores that could survive the constant reshaping of Earth's surface. Regions such as the Canadian Shield, the Fenno-Scandinavian Shield, and the Pilbara Craton in Australia stand as living fossils of this era. Their rocks record some of the oldest known life, preserved in the form of stromatolites and chemical signatures indicating microbial activity. These continental cores not only preserved Earth's geological history, but also provided the physical stability necessary for life to continue evolving. By this time, the atmosphere had begun to change subtly. Cyanobacteria, living in shallow seas along the stable cratons, were releasing oxygen as a byproduct of photosynthesis. This slow but persistent oxygenation would eventually contribute to the Great Oxygenation Event hundreds of millions of years later. The interplay between solid, stable land and life in these shallow seas created feedback loops that reshaped both the planet's geology and its biology. Supercontinents such as Columbia began to form as cratons slowly collided and merged. These supercontinents were dynamic, with repeated cycles of rifting and collision reshaping the planetary surface. The emergence of Columbia marked a significant milestone. Earth now had vast, stable landmasses that could last for hundreds of millions of years, offering habitats for microbial communities, influencing ocean currents, and changing atmospheric patterns. The importance of this stability cannot be overstated. Without these enduring continental cores, life would have remained confined to isolated niches, constantly disrupted by geological chaos. With large, stable landmasses, Earth now had the scaffolding to support complex chemical cycles, nutrient accumulation, and eventually the rise of multicellular life. Rivers began to carve valleys, depositing sediments into shallow seas, while erosion and weathering provided essential minerals to the oceans. In essence, Earth had transformed from a chaotic, molten world into a structured planet with the first enduring continental landscapes capable of supporting long-term biological activity. By the end of this era, approximately 1 billion years ago, Earth's continents had evolved from scattered, fragile islands into cohesive, stable landmasses. These shields would act as the building blocks for the next supercontinent, Rodinia, shaping not only the planet's geology, but also its biological destiny. The late Precambrian period therefore represents a critical turning point in Earth's history, a time when the planet's solid crust matured,
ecosystems began to stabilize, and the stage was set for the dramatic evolutionary changes to come.
By approximately 1 billion years ago, the Earth had entered a period of profound transformation. The scattered cratons and smaller continental fragments of the late Precambrian were now converging, forming one of Earth's most significant supercontinents, Rodinia. This supercontinent was not merely a collection of landmasses. It represented a massive geological experiment, shaping Earth's tectonics, climate, oceans, and habitats available for life. The process of Rodinia's formation was gradual and violent. Tectonic plates, carrying stable cratons across the globe, collided over tens of millions of years. Mountains rose where plates converged, while shallow seas and rift valleys formed where plates were pulled apart. Massive volcanic activity accompanied these collisions, releasing heat and gases into the atmosphere. These geological upheavals, while catastrophic on a local scale, laid the groundwork for a stable, interconnected landmass that would influence Earth's systems for hundreds of millions of years. Rodinia's formation had a profound effect on the planet's climate and ocean circulation. With a supercontinent occupying much of the equatorial and mid-latitude regions, wind patterns shifted and ocean currents were redirected. These changes affected global temperatures, weather patterns, and nutrient distribution in the seas. Shallow coastal regions along Rodinia's margins became hotspots for microbial life, where stromatolites and cyanobacteria thrived in nutrient-rich waters. The emergence of these vast landmasses and the accompanying shallow seas created the first complex environmental feedback loops, linking tectonics, climate, and biology. Life during this time remained microscopic, but its diversity and complexity were increasing. Microbial mats formed layered structures, producing oxygen through photosynthesis. This incremental oxygen production gradually altered Earth's atmosphere, setting the stage for the eventual proliferation of multicellular life. The stability of Rodinia's landmasses provided long-lasting coastlines and shallow seas, which acted as protective incubators for early ecosystems, allowing life to experiment with new strategies for survival, reproduction, and energy capture. Rodinia's story was also one of tension. While the supercontinent unified much of Earth's crust, internal pressures and heat buildup in the mantle created zones of rifting and future instability. These early rift zones hinted at Rodinia's eventual fragmentation, a process that would recycle nutrients, reshape ocean basins, and pave the way for the next supercontinent cycle. The interplay between formation and eventual breakup of Rodinia exemplifies the dynamic nature of our planet, a constant push and pull between construction and destruction. By the end of Rodinia's formation, the Earth had evolved into a planet with vast, interconnected landmasses and complex life-sustaining environments. The supercontinent served as a laboratory for life, where the combination of stable land, shallow seas, and changing atmospheric conditions allowed evolution to experiment in ways previously impossible. Though no plants or animals existed yet, the microbial world thrived, setting the foundation for the explosion of life in the following eons. Rodinia's existence, though transient in geological terms, had lasting consequences. Its formation influenced tectonic patterns for billions of years, shaped the evolution of Earth's crust, and created environmental niches crucial for the survival and diversification of life. It was a reminder that the Earth's surface is never static, and that the continents themselves are living entities, constantly moving, colliding, and reshaping the destiny of life on our planet.
As Rodinia stabilized around 1 billion years ago, Earth had entered a remarkable new phase. The supercontinent's presence dominated planetary dynamics, influencing climate, ocean circulation, and even the distribution of life. While microbial life thrived along its vast coastal zones and shallow inland seas, the planet itself was undergoing constant change beneath the surface. Rodinia, despite its impressive size and stability, was not permanent. Deep mantle heat accumulated, tectonic stresses increased, and rift zones began to form along its edges. These zones foreshadowed the eventual fragmentation of the supercontinent. Over the next hundreds of millions of years, Rodinia would break apart into smaller landmasses, which would drift and collide again to form subsequent supercontinents. This endless cycle of formation and fragmentation illustrates Earth's dynamic nature, a planet constantly reshaping itself, providing new habitats and influencing evolutionary pathways. The late Precambrian period also witnessed dramatic shifts in the environment. Shallow seas teeming with microbial mats and cyanobacteria produced oxygen that slowly accumulated in the atmosphere. This gradual oxygenation set the stage for the Great Oxygenation Event, which would fundamentally alter the composition of the atmosphere and enable the future evolution of more complex life. The interaction between stable continental masses, shallow nutrient-rich seas, and the evolving atmosphere created a delicate balance, where geological processes directly influenced biological evolution. The supercontinent cycles of assembly and breakup also had profound implications for Earth's climate. Vast land masses at varying latitudes influenced wind patterns, ocean currents, and global temperature gradients. Ice ages would periodically occur, reshaping continents, carving valleys, and redistributing sediments. These climatic and geological pressures acted as selective forces on early life, encouraging adaptation, diversification, and eventually the emergence of multicellular organisms. As we observe these ancient events today through geological records and fossilized microbial structures, we gain insight into how the Earth's crust evolved, how continents stabilized, and how life adapted to a planet in constant motion. The story of Rodinia, though set in a time billions of years ago, resonates through Earth's history. It illustrates the interplay of tectonics, climate, and life, a cycle that would continue through the formation of supercontinents like Pannotia, Gondwana, and eventually the modern continents we recognize today. For modern viewers, understanding Rodinia's formation is more than just a lesson in ancient geology. It is a demonstration of Earth's resilience, adaptability, and the interconnectedness of life and land. The early microbial ecosystems thriving in these primordial conditions were the foundation for all subsequent biological innovation. From these simple organisms emerged the building blocks of complexity, paving the way for plants, animals, and ultimately humans. This episode marks the culmination of a critical chapter in Earth's history. From the first life forms appearing in shallow seas to the growth of cratons, the assembly of Kenorland and Columbia, and the dramatic formation of Rodinia, we have traced the journey of our planet's early continents. Each supercontinent not only shaped the physical world, but also influenced the evolutionary trajectory of life. As Rodinia fragmented and Earth's continents continued their slow, inexorable drift, the stage was set for the next era, the rise of more complex ecosystems, the eventual colonization of land, and the diversification of life that would lead to the modern continents teeming with flora and fauna. In the next playlist, we will explore how these landmasses evolved through the ages, the climatic shifts that shaped them, and the emergence of complex life forms that eventually paved the way for humans. This concludes our journey through the first billion years of continental evolution. Rodinia stands as a testament to Earth's dynamic history, illustrating that even in the most ancient times, the planet was alive, reshaping itself and nurturing life in ways that continue to resonate to this day.